Hello, everyone. My name is Martin Lonsky, and I'm from the Material Science and Engineering Department of the University of Illinois at Urbana-Champaign. I would like to welcome you to my presentation, where I'm going to talk about how to tune the magnetic properties of novel platinum, cobalt, manganese multilayers. To give a short introduction into this topic, I would like to motivate this work by considering skyrmions in magnetic multilayers. And to do that, I would like to introduce the two main energy terms that are relevant here. The first one being the exchange interaction term, which is also called symmetric exchange. So if we have two spins, Si and Sj, which are usually neighboring spins, depending on the sign of this so-called exchange constant, the spins like to be in a parallel or anti-parallel state, and thereby the sign of J determines whether a material is a ferro or antiferromagnet. So far, so good, but there exists another type of exchange interaction, which is antisymmetric, the so-called Dzieloszynski-Moria interaction, or DMI. Here, the spins prefer a perpendicular orientation with respect to each other, because Si and Sj are in this cross product, so Si and Sj preferably would be perpendicular in contrast to the symmetric exchange interaction. Okay, and now if we combine these two energy terms or interactions, we usually end up with states like helical spirals, or under certain conditions, we can also get something called skyrmions, which are these tiny magnetic whorls here that are topologically distinct. Some pictures of those are shown here. And a very suitable system to observe skyrmions are multilayers. The first reason is that in this material system, skyrmions have been observed even at room temperature. And also magnetic multilayers possess the advantage that their magnetic properties are highly tunable, as we will also see for the present material system, namely platinum, cobalt, manganese. If you're interested in skyrmions in magnetic multilayers, please take a look at this very nice review paper here. But now I would like to focus more on platinum cobalt metal multilayers in particular. So here I give a short overview of the current state of literature. Platinum cobalt, of course, is well known for a very long time already. But if we add a third metallic layer to platinum and cobalt, we may obtain a reasonably sized DMI, as it's shown in this table for different combinations with different materials, from a very recent manuscript here on arXiv. And as you can see, there is a DMI in each of those cases. These are numerous systems, and there are many more in other papers that have already been studied, but nobody has taken a look at platinum, cobalt, manganese yet. And we thought that manganese would be a natural addition to this already existing set of platinum, cobalt, metal multilayers. Here are two different material systems, and different types of imaging techniques have been used to visualize the different magnetic states. So usually you have something like a labyrinth-like domain pattern. And if you apply magnetic fields, or if you apply electric currents or current pulses, then you might end up with a disordered or even ordered phase of magnetic skyrmions, as it's shown here, or here in this very nice Lorentz TM measurements. In our case, as I mentioned, we have fabricated platinum, cobalt, manganese multilayers. So these are the methods that we have used. For the fabrication, we used magnetron sputtering at relatively low powers so that we can reliably get those very small thicknesses here for the individual layers. We have used argon atmosphere of a 3 millitorr in each case, a relatively low base pressure, and everything has been done at room temperature. Structural characterization has been performed via X-ray reflectometry, XRR, while we still plan to do TM measurements in the near future. Magnetic properties have been measured with the MPMS by quantum design. That means mainly SQUID or VSM measurements. And we have our own home-built Kerr microscope to perform MOC or magneto-optical measurements of the different samples that we are looking at here. So here on the first slides with results, I would like to convince you that all of our multilayers are of a very high quality. These are 4 diagrams for a different number of repetitions of this trilayer, platinum, cobalt, manganese. And you can see that the experimental data shown in different colors and the fit to these data are in very good agreement. And this means that our samples are of high quality. And also another indications for that is that the interfacial roughness is at most 3 angstrom for all of these samples. As I mentioned, we still want to perform TEM measurements soon in order to make sure that these layers are well separated, or if we have intermixing of adjacent layers, for example. So regarding the magnetic characterization, we have recorded magnetic hysteresis loops here with a field applied out of the plane of the multi-layer system. Here is shown the magnetic moment as a function of the magnetic field for, again, the same samples with different number of repetitions. You can see actually that there's a systematic behavior for the out-of-plane measurements as a function of repetition number, and also for in-plane. There is also a very systematic behavior. And if you compare these two diagrams, you can see that we have a clear evidence for an out-of-plane anisotropy. And also what is very encouraging is the shape of the hysteresis loops here in the out-of-plane case is very typical for Skyrmion hosting films, as you can see here on these two pockets in this orange curve, for example. Okay, and everything is relatively systematic. So if we vary the cobalt thickness in our films here shown for the case of 2 repetitions, you can see that we have a strong out-of-plane anisotropy for low cobalt thickness, going towards an in-plane anisotropy for higher cobalt thicknesses, and everything in between might be interesting for the formation of skyrmions here, and also for the varying thickness of manganese. Here again, for n equals 2, we can see a systematic behavior. The shape of the hysteresis loop changes, and also the saturation magnetization is actually reduced, which is very interesting and might be related to antiferromagnetism being present due to the manganese, or maybe even due to the interaction or intermixing of manganese and cobalt, I should say. This is also true for a higher number of repetition, here shown for 3 different samples with different manganese thickness. And in order to understand that a little better, we have performed temperature-dependent hysteresis curve measurements, plotting here the coercivity against temperature. And you can see that when no manganese is present in the platinum cobalt samples, or tantalum instead of manganese, there is not much happening with the coercive field here. But if we have thicker and thicker manganese layers, actually what happens is that there is a strong increase of the coercivity, indicating the presence of antiferromagnetic coupling, or even some kind of spin glass phase here, at least at low temperatures. And that may be, again, due to the intermixing of cobalt and manganese, for example. And that's why we think TEM measurements would be very useful in the near future. You can see that there's even a maximum in the coercivity here at manganese thicknesses of around 1.5 nanometers. The MOC measurements are also very interesting. First of all, for varying manganese thickness, for low thicknesses, you can see these domain patterns here for n equals 2 again. So here the domains are large enough that they can be visualized in our MOC. If we use a higher number of repetitions, that becomes difficult. And if we increase the manganese thickness, you can see that we obtain something that looks like potentially skyrmions, or at least some bubble-like domains, which is hard to distinguish here with the measurements that we have performed so far. Also, as a function of the cobalt thickness, everything is systematic here. So here is shown some images for increase in cobalt thickness. And actually what also is interesting is that these two pictures, for example, have been acquired at the same magnetic field, almost at 0 field, after saturation at the high out-of-plane field. So there is a slow dynamics changing the domain pattern without even changing the magnetic field. And this is visualized here once again with this hysteresis curve. So we saturate the sample, then sweep the field down to 0 or to a very small field value, wait for a long enough time, and see that there is this S-shaped change of the magnetic moment as a function of time, turning into linear behavior here at higher times. And this is in good agreement with previous measurements on platinum cobalt that have been published here. So to summarize, we have looked at a novel multilayer system, platinum cobalt manganese, that has been fabricated by sputtering, and we had samples of very good quality. We have a systematic dependence on the cobalt and manganese thickness in the hysteresis curves. Temperature-dependent data indicates the presence of antiferromagnetism related to manganese or even intermixing of manganese with cobalt. And we have first indications for the presence of skyrmions, or at least magnetic bubbles. And also finally, the slow domain dynamics as seen in the MOG and also MPMS measurements. With that, I would like to thank you for your attention, and I'm happy to take any questions that you might have.